Hi, so in this second video of our tropical cyclone formation series, we're going to take a look at two different paradigms for vorticity or vortex development. Top-down, that takes our mid-level vortex developed in the previous discussion and brings that down toward the surface. And bottom-up, that develops low-level cyclonic rotation and builds that up within the cocoon of the mid-level vortex that we have previously developed. So let's dig in. So recalling from our last video, we introduced this idea of an observational perspective on tropical cyclone formation with two distinct stages. Stage 1, characterized by mid-tropospheric moistening and mid-tropospheric vortex development that radically transforms the vertical thermodynamic profile, temperature, but especially moisture, to permit convective redevelopment and persistence, in particular in Stage 2. It also led to the development of a mid-level vortex here due to the heating profile associated with the thunderstorms that took place during stage 1, with warming over much of the troposphere and cooling over a shallow near-surface layer just above the ground. And so in this video, we start with this mid-level vortex that is present at the end of stage 1, at the beginning of stage 2. And rather than looking at the thermodynamic and specifically the thunderstorm evolution going through stage 2 to tropical cyclone formation, we're going to take a look at the rotational aspects, the vorticity or vortex aspects associated with this mid-level vortex and how we go from that structure to a structure with rotation that is maximized at low levels. So we seek to ask the question, how exactly do we get strong low-level cyclonic rotation? And this is where our two paradigms that we introduced before, this idea of top-down and bottom-up, come into play. I want to emphasize right now, these are not mutually exclusive paradigms. Elements of each can be true at the same time. They are not necessarily in conflict with each other, but they're two distinct ways, top-down to bottom-up, to look at the process. They have different emphases in terms of the role of the mid-level vortex and the role of thunderstorm activity for the development process. Top-down emphasizes a direct role of this mid-level vortex. Specifically, the evaporation-driven downdraft that we get at the end of stage 1. Not only does it build a mid-level vortex, but it advects it downward into the atmospheric boundary layer, so down toward low levels. It's still weaker at low levels than what you see at upper levels in the mid-troposphere, but you do have cyclonic rotation extending down toward the low levels due to this advection by the evaporatively driven downdraft with the decaying thunderstorms. Then, when you go into stage 2, you've rewarmed and humidified the boundary layer. You get thunderstorms erupting on a scale of the vortex. So not individual thunderstorms here, but a big mass of thunderstorms on the scale of the vortex. And the vertical profile of vertical motion associated with these thunderstorms stretches that low-level rotation and leads to its amplification preferentially near to the surface as you build the vortex upward from there. So the direct role of the mid-level vortex is to bring rotation down to the low levels where thunderstorms that develop within its cocoon can help to amplify that from the bottom up. Whereas this bottom-up idea really emphasizes a supplemental role of the mid-level vortex. That vortex exists as a cocoon or embryo or pouch, as the meteorological phrasing gives it, in which thunderstorms develop and they generate localized, so on the thunderstorm scale, not the big vortex scale at this point, but the individual thunderstorm scale, strong low-level cyclonic rotation. And the convergent cyclonic circulation brings all of that together, and these strong updrafts help spread that vertically and congeal it into a cohesive mass that we know as a vortex scale feature or a tropical cyclone specifically. We could also phrase these roles as being sort of a passive role for thunderstorms in the top down and a very active role for thunderstorms in the bottom up. Whereas we're looking at a more active role for the mid-level vortex in the top down and a supplemental role in the bottom up. So let's dive in and discuss a little bit more about each. So in terms of this top-down formation here, this part A, the top panel on our figure at left here, is really the very beginning of thunderstorm activity in stage 1 of our observational perspective. And B is the crux of stage 1 of our observational perspective. So our initial thunderstorms have a downdraft. Precipitation falls out and evaporates, and it's that cooling, that formation of that dense air relative to the surroundings that drives that downward toward the surface. It reaches the surface and spreads out. So our heating profile with low-level cooling and mid to upper-level warming create this mid-level mesocyclone or mid-level vortex, mesoscale convective vortex. And this downdraft advects that downward toward low levels. In addition, as we described in our previous video, it cools and humidifies the lower troposphere, this middle point here on the middle panel at left. It dries the lower troposphere, but it really humidifies it as it cools it as well. Then these surface energy fluxes, enthalpy in the form of sensible and latent heat, which we can measure through moist static energy, we can measure through equivalent potential temperature, which relates to both of which relate to temperature and moisture, recover as you get heat directed from the warm, moist ocean below to the relatively cool, relatively dry in terms of saturation specific humidity or specific humidity more generally, atmosphere residing above. And this helps that boundary layer air to recover, just as we talked about in our previous video. This allows for thunderstorms to redevelop within this vortex environment, strong mid-level rotation and weaker low-level cyclonic rotation. Once this happens, with convergence maximized at low to mid levels with that cyclonic rotation that we have here at stage or panel B at the end of stage 1 and going into stage 2, ascent is maximized. Recall that relationship between convergence and divergence and vertical motion. Low-level convergence leads to ascent that increases upward as you get to that level of non-divergence. And then if you have divergence aloft, your ascent is going to begin to weaken as you go up further from there. So within this embryo fostered by the mid-level vortex, you have this large-scale rising motion that gets stronger as you go up into the middle troposphere, fostered by the pattern of convergence facilitated by the low and mid-level vortex. And this helps to take that low-level cyclonic rotation and stretch it out in the vertical. And just like the figure skater, stretching it out in the vertical causes its rotation rate to increase. And we call this vortex stretching or vortex tube stretching, depending on the phrasing. So let's take a look at this from a mathematical and dynamical perspective here. So we have our thunderstorm that we depicted in cartoon form in our previous video. We have mid-level rotation maximized here and weak low-level cyclonic rotation maximized here. I have a pattern of vertical velocity depicted here by the red line at right. So vertical velocity magnitude is on the x-axis and height here is on the y-axis. So giving rise to this, we can imagine weak low-level convergence that gets slightly stronger as you go up through to the mid-troposphere here, where we have our level of non-divergence where it comes back towards zero. That's where our vertical velocity is maximized. And then as we have mid to upper level divergence atop that, that vertical integration goes closer and closer to zero, bringing us back to no vertical velocity by the top of the cloud, near to the tropopause. So low level convergence, that becomes stronger and then becomes weaker, back to zero, leads to our ascent maximum at mid levels, and then mid to upper level divergence, it becomes stronger and then comes back towards zero, leads to our vertical velocity going back towards zero here. So we can express mathematically how rotation, here measured by zeta for relative vorticity, which is just a measure of the rotation in the horizontal xy plane, changes following the 3D flow. Note the capital D's that we see here on the left-hand side. So we're following the air along. This changes as a function of two different terms. This complicated, nasty-looking term here that has an omega sub h dotted into the gradient of w in the horizontal plane. We'll come back to that term when we get to the bottom-up formation later on in this video. But we really want to focus on this right-hand side term here. This eta that we see here is our absolute vorticity. It's a combination of this relative vorticity, which is that rotation in the xy plane, plus the Coriolis parameter, which is a measure of rotation associated with the Earth's rotation. So you can think of it as a total horizontal vorticity or horizontal rotation, so to speak. We have the product of that with the vertical change of the vertical velocity here, which we can diagnose from the chart that we see here. Note that the greatest gradient of vertical velocity increasing upward is found here in the lower troposphere. It then becomes near zero into the middle troposphere, and then it becomes negative as you get to the upper troposphere. So at low levels here, which we'll add in the diagnostic here, the partial derivative of vertical velocity with height is positive. Because we're dealing with cyclonic rotation, relative vorticity is positive. And in the northern hemisphere, absolute vorticity is positive. They're both positive for cyclonic rotation in the northern hemisphere. So these two terms are both positive, which means that the left-hand side is going to be positive, which means that cyclonic rotation is increasing following the wind, which means that if you have a low-level cyclonic vortex with a stronger mid-level cyclonic vortex, what you're going to do through this formulation is as that vortex moves along, this vertical profile of vertical motion is going to stretch out that rotation, maximizing it at low levels, decreasing it as you go upward from there, ultimately leading to negative values as you get to the upper portion of the troposphere here, giving us our warm core tropical cyclone structure. Strongest cyclonic rotation at low levels that then decreases as you go upward from there. Let's contrast this to bottom-up formulation here. So we have a 12-panel figure here where each panel is 3 hours different from a numerical model simulation of tropical cyclone formation. And what we have shaded here is 850 millibar relative vorticity, or that measure of cyclonic rotation. We have positive values shaded times 10 to the minus fourth inverse seconds here. So warmer colors denote more intense cyclonic rotation. And note here in the first couple of rows of panels, you have individual maxima about this broader circular area in terms of the contours here, which depict a measure of the height anomaly associated with the feature. So about this broader scale negative height anomaly, we see individual cyclonic vorticity or cyclonic rotation maxima. But over time, these not only become more intense, but they merge together into a cohesive whole near to the center of the disturbance. And this is what leads to the formation of a tropical cyclone. So within this bottom-up formulation paradigm, we still need that rewarming and remoistening of the atmospheric boundary layer that occurs as you go from stage 1 into stage 2. This allows for thunderstorms to redevelop, and this occurs with that mid-level vortex. But in this formulation, that mid-level vortex serves mostly as an isolating feature from the surrounding environment. We talked about the mid-level vortex in our last video, increasing that inertial constraint, helping to keep air on the outside out and on the inside in. So the bottom-up formation paradigm insists on this occurring. We keep the air within the cyclonic circulation within the cyclonic circulation. And it's within this circulation that these thunderstorms redevelop, and they're on the individual thunderstorm scale. Each one of these is associated with localized strong low-level cyclonic rotation. You can see these orange and yellow maxima within many of the panels in the first 2 to 3 rows here until we get to about 102 hours. Each one of these is a localized maximum of low-level cyclonic rotation, and we call these things vortical hot towers. Vortical like vorticity, so it's a vorticity-laden hot, given the fact that convection or thunderstorms tend to warm relative to their surroundings. Tower, given that it's a deep vertical feature that we see within the troposphere. So over time, so long as the disturbance remains relatively isolated from its surroundings, these individual vortical hot towers, individual thunderstorm-induced vorticity maxima merge together into a coherent vortex, this bottom row of images that we see here that we know is our tropical cyclone. So coming back to our cartoon of a thunderstorm here, we have the rotation structure that we see at the end of stage 1 and beginning of stage 2. Our mid-level vortex is located here. We have weaker cyclonic rotation below and weaker cyclonic rotation above. Thus, if we think about a wind coming out of the screen here on the left and into the screen here on the right, it's less out of the screen above and below the mid-level maximum than it is at the mid-level maximum. And conversely, on the other side, it's more into the screen at the mid-level maximum and less above and below that. So there's a vertical shear, a change in wind speed with height from the low levels to the mid-level vortex and from the mid-level vortex upward from there. So this results in what we call horizontal vorticity. And this is where some of the vorticity terminology is really kind of wonky. The rotation that we're used to is on the XY plane. You can look down on the Earth, north, south, east, west, and you see rotation like with a cyclone, tropical or otherwise. That is what we refer to typically as vorticity, relative vorticity, but in terms of a mathematical formulation, that's actually known as the vertical vorticity. Vertical being the z-plane, and if you have a line in the z-axis, the rotation is in the xy plane around that feature. Here we have what is known as horizontal vorticity, that instead of your plane being the z or vertical axis, instead it's the x or the y axis, and you have rotation around that plane. So we're looking at horizontal vorticity as rotation on an xz or yz plane. So if we envision this being the y-axis going into the board here, or into the screen, you have strong flow to the north here, weak flow to the north here, weak flow to the north down here. So you get flow that's faster to the north, and if you put a stick in the wind here at low levels, it's going to turn like so in this YZ plane. The flow is on the y-axis and the z-axis relative to the x-axis that runs through it. It's a little bit difficult to visualize. We'll take a closer look at it here on the next slide. This horizontal vorticity is all fine and good, but it's not the rotation we see with a tropical cyclone. But this thunderstorm updraft, as we'll show on the next slide, can actually tilt. I apologize for that getting cut off by my screen there, but it can tilt. It can take that rotation in this XZ or YZ plane and put it into the XY plane that we're used to for cyclonic rotation and lead to the amplification of low-level cyclonic rotation that way. So what does that look like? So let's take this left part of the schematic here at first. We have vertical wind shear here. This is around 4 kilometers, 600 to 700 hectopascals, and we're looking at strong flow, in this case from right to left here, and it's weaker above and below. And so these two little rotations that you see in the upper and lower part of the diagram are associated with the stick in the wind there. If you put a stick in the wind right here, the top of it's going to turn to the left and the bottom is going to turn to the right. If you put a stick in the wind here, the bottom of it's going to go to the left and the top of it's going to come back around to the right. And that's what we see in terms of the directions of these circulations here. These are horizontal vorticity. We can use a visual aid known as a vortex line, these purple lines that we see here that go through them. So think of each one of these as a hula hoop, for instance, that you're sticking your arm through, ultimately speaking. It points in the direction away from you when that hula hoop is rotating clockwise from your perspective. So if you're back here looking at the hula hoop rotating clockwise, that line is going through it and away from you. Whereas if you're over here and looking at the hula hoop and it's rotating in the opposite direction, that line is coming towards you in that frame of reference. So that's all fine and good, but let's say we take this feature here or this feature here and put an updraft through it. So let's take a thunderstorm updraft and put it through that vortex line, which is our visual representation of this horizontal vorticity. We tilt that line. We take this horizontal line and we end up tilting it like so. And on either side of that updraft, one here and one here, you get the different senses of rotation. So in this case, this line that's pointing from left to right is associated with rotation coming around like this. But if you take that line and tilt it like so, you get cyclonic rotation on the left and anticyclonic rotation on the right. The opposite is true for the other vortex line that we see here, because the sense of rotation is different. It's going this way here, and if you tilt that up within the vertical, you get anticyclonic rotation here on the left and cyclonic rotation here on the right. It's a bit easier, though I'm not saying easy, to visualize it in this context rather than breaking out the math, looking at the horizontal vorticity vector, each term of which has multiple partial derivatives, that you then take the dot product into another partial derivative of the vertical velocity. You get a really nasty looking set of terms here. So I encourage you to take a little bit of time and think about this idea of stick in the wind that leads to different senses of rotation, and this idea of a vortex line, an arm through a hula hoop, for instance, and how tilting that up into the vertical can lead to these different senses of rotation that we see here. So this is all fine and good, but what do? You have a positive and a negative, cyclonic and anticyclonic and cyclonic in either one of these cases. To be able to amplify the cyclonic, once you've tilted this into the vertical, you need to be able to have some sort of wind bring this cyclonic couplet, cyclonic vortex, cyclonic rotation underneath the updraft, where that same stretching term that we looked at for the mid-level vortex in the top-down paradigm can then stretch that vertically as well. So it's a combination. It's not just this tilting associated with this change in intensity of the mid-level vortex that we see here in panel A, but once you've tilted that rotation into this XY plane, anticyclonic and cyclonic alike, you then have to bring that cyclonic underneath the updraft for that to be able to be stretched out and amplify it from there. So re-emphasizing using this as an opportunity to close, the paradigms are not mutually exclusive to each other. There are elements that are common to both paradigms that are supported by observations, theory, and numerical model simulations. And these include things like mid-tropospheric moistening to make the atmosphere resilient against downdrafts to prevent convective longevity and persistence. Isolation of the disturbance from its cooler, drier environment. They both emphasize the role of the mid-level vortex in that regard. You don't want to bring in cooler, drier air from the surroundings and thus lead to convection dissipating and leading to further evaporatively driven downdrafts. They both require boundary layer recovery from surface heat fluxes, moisture and heat, facilitating thunderstorm redevelopment. So you need thunderstorms to occur in both cases. One paradigm emphasizes the system scale set of thunderstorms, and the other emphasizes individual thunderstorms. They also emphasize the organization of individual thunderstorms into a cohesive unit. The top-down starts with that as the outcome. The bottom-up brings individual ones together over time into a cohesive unit, but they both get there eventually. And they both relate to thunderstorm and vortex scale rotation amplifying. The top-down looks at thunderstorms on that vortex scale, so they're occurring concurrently, whereas the bottom-up is amplifying it first on the thunderstorm scale, and then as it merges together, amplifying it on the vortex scale. So in this sense, the two paradigms suggest that the mid-level vortex plays both direct and supporting roles or indirect roles in facilitating tropical cyclone formation. The isolation is an indirect role. The organization of thunderstorms is an indirect role. The vorticity here, especially in terms of the thunderstorm scale, is more of a direct role. Whether or not it actually comes down to the boundary layer through advection, as the top-down paradigm would suggest, is perhaps an open and debatable question. There's not a ton of evidence for that specifically. But you can see elements of both direct and supporting roles for that mid-level vortex through this listing that we see here. The key difference, however, when you get to going from the outcome of the top-down or the bottom-up paradigm to the actual tropical cyclone, is the fuel for the tropical cyclone energy gained from the ocean in the form of surface sensible and latent heat fluxes, or enthalpy fluxes, combining them into one, or by an upscale vorticity rotation energy cascade from the thunderstorm scales. So what is that role of thunderstorms? Is it a vorticity driven role where the energy is tied to the vorticity of individual thunderstorm elements that come together and grow into a bigger intense vortex? Or is it that the thunderstorms play that passive role? They form, and they're needed to form to be able to take the heating from the underlying ocean and spread that through the vertical and create a warm, moist, isolated disturbance relative to the surrounding environment. Observations in theory and numerical model simulations suggest that it's primarily the latter, that more passive role. That thunderstorms are crucial. They spread that heat over the vertical, but it is the heating gained from the underlying ocean that is ultimately the critical distinguishing factor that fuels the tropical cyclones. This is tied to a wind-induced surface heat exchange that will form the basis for our next video and our last video in this series. How does this energy gained from the underlying ocean go into actually fueling the tropical cyclone? Not as much when it is developing, but rather after it has formed and is subsequently intensifying. So that'll be the focus of our last video in this series. But until then, thanks for tuning in.